In the last class, we discussed about the applications of Nernst equation. Another important application which you need to notice is about concentration cells. All right. So today we'll emphasize more on the concentration cells. Everybody, check it out. In galvanic cells, if both electrodes are same, then we call it as concentration cell. In short, the E naught cell should be equal to 0. Okay. Now, in the EMF of the cell depends upon concentration of different chemical species participating in the redox reaction. Okay. In that case, it is an electrolytic concentration cell. Okay. What does that mean? Basically, if concentration is the part which is playing the role here, sorry, difference in the concentration is the part that is playing the role here to give some amount of E cell value, then those are electrolytic concentration cells. It also depends on the pressure of the gas, then it is known as electrode concentration cell. Okay. If by chance there is a pressure difference, then we call it as electrode concentration cells. Eventually, they are basically, they are concentration cells altogether. Let me show you with an example. Suppose if on the anode side I have a gas electrode, on the cathode side I have a similar gas electrode, but the gases are maintained at different pressures and concentrations of the solutions are maintained at different pressures. Then what will be the oxidation half reaction and what will be the reduction half reaction? Let me write on that. The oxidation half reaction being H2 gas is converting into 2H plus 2 electrons. Here pressure is P1, concentration is C1. While if we write the RHR, it is going to be 2H plus 2 electrons is giving H2 gas. In that case, here concentration is C2, pressure here is P2. Okay. Now, we know one thing that E naught cell of this overall cell is 0. Then E cell as per Nernst equation, which is E naught cell minus 0.0591 by N log of Q. So in that part, this is 0. So E cell will be equal to minus 0.0591 by 2 in this case, log of Q. For Q, we require to write the overall reaction here. And you can see overall reaction is H2 plus 2H plus is giving 2H plus H2. And H2 here is P1 and here it is P2. This is C2 and this is C1. So Q will be equal to C1 square and then P2 by C2 square and then P1. Isn't it? This is what you will get. So therefore, E cell will be equal to minus 0.06 by 2 log of C1 square P2 by C2 square P1. So now there is two level of understanding that you need to know. At constant pressure on both sides, or sorry, same pressure, I should not say constant pressure, at same pressure, okay, you know that Q will be equal to C1 by C2 whole square, which implies if C1, which is basically the anode concentration, if it is greater than C2, which is the cathode concentration, then cell will be non-spontaneous. Cell will be non-spontaneous. Why? Because E naught cell will be equal to, will be less than 0. Similarly, at same pressure, if C2 is greater than C1, then Q will be less than 1, which implies E naught cell will be greater than 0, which implies cell will be spontaneous. So generally, if the cathode ion concentration is more and anode ion concentration is less, you will get a spontaneous cell using this concentration cell. Okay. So I hope this understanding is clear to everyone. So in short, concentration cell is a cell where we have same electrodes but maintained at different concentration or different pressures. Same logic we can do it for pressures also. At same concentrations at anode and cathode, if P1 is greater than P2, and what is P1? P1 is the anode side partial pressure. If that is greater than cathode side partial pressure, then Q will be less than 0, which implies E cell will be greater than 0, which implies cell will be spontaneous. Cell will act spontaneous. Okay. So I hope you understood which concentrations increasing or decreasing will make cell being spontaneous. Okay. Now let's come to this question here. Of course, this is not the usual concentration cell question. We'll go with some cases first. See, in case if there is a normal cell given here and we have been used the question as what is the value of K equilibrium. In such case, what we do? See here, the minute you are expecting that you are to figure out the K equilibrium, that is only possible when E cell is equal to 0. That means that is this cell is at equilibrium. Equilibrium as in we are not able to see any movement of electrons from anode to cathode. Okay, which means E naught cell will be equal to 0.0591 by n log of K equilibrium. Okay, and if I write this as the overall equation here, zinc is oxidizing itself into Zn2 plus 2 electrons. Iron is getting reduced to Fe, and overall reaction is zinc plus Fe2 plus is becoming Zn2 plus Fe. So that implies Q will be equal to Zn2 plus by Fe2 plus. So Q will be equal to 10, 10 raised to power of minus 2 by 10 raised to power of minus 3, which is equal to 10. Sorry, I would not use the word Q anymore. It is K equilibrium. So K equilibrium value is 10, which implies E naught cell will be equal to 0.0591 by 2 log of 10, which is 1. So 0.06 by 2, approximately 0.03 volts. It is positive, so it is a spontaneous cell as well. Clear? Okay. Okay. Now I made one mistake here. So here EMF of the cell is given. Calculate the value of K equilibrium for the given cell. Got it? This is assuming E naught cell is 0 at this particular value, isn't it? I was assuming that this is the K, these are the concentrations at equilibrium. Correct? But what if there is an E cell given already, and then you have to find out what is the value of K equilibrium at this position. So for that, we require to get E naught cell value. Here, E naught cell value is what we calculated, correct? So, well, since we calculated already, I just have to change this part as only Q here, uh, Q here, correct? And this one I'll write as Q here. So we got what is the E naught cell value, and E cell value is known to us, which is 0.3, 0.3. Okay. So when this is E cell being 0.3, then E naught cell value will be equal to, uh, let me write down that in the equation here. Sorry, that is E cell is equal to E naught cell minus 0.0591 by n log of Q. So E cell will be this entire value which we calculated plus E cell. Okay. So we just have to add that to E cell here. So I will just make that addition here plus E cell here. Okay. As this value will be, this value is what we need to calculate. So let me just write down that part. This plus E cell. E cell value is given as 0.3. So that makes it 0.33 volts. This is the E naught cell value. E naught cell value is 0.33 volts. And now you put this E naught cell value, correct? And then figure out what is K equilibrium. So therefore, E naught cell value, which is equal to 0.0591 by 2 log of K equilibrium plus 0, because at equilibrium this E cell now will become 0. So therefore, this will be equal to 0.06 by 2 into log of K equilibrium is equal to 0.33 volts. So log of K equilibrium will be equal to 0.33 by 0.03. Isn't it? This is what we will get. 0.33 by 0.03. So therefore, from here, we will get this as 11. Okay. So you can see 3, 3. So 1 second. We got 0.3 here, 0.03, 0.33 here. I was getting 11. Correct. I'm getting 11 only. That implies K equilibrium value will be equal to 10 raised to power of 11. This is how much you will get. Please check once, everybody. Sorry, done everybody? Shall we go ahead? Right. See this next question now. How much amount of copper 2 plus is present at equilibrium when excess amount of finely divided nickel metal is added with 0.05 molar in and mixed 0.05 molar is mixed with the solution of copper sulfate. Okay. So we need to find out. I mean, the reaction what it is happening is like this. That is copper 2 plus nickel. Okay. That is converting into nickel 2 plus aqueous plus copper solid. So nickel is getting oxidized in the presence of copper 2 plus and copper 2 plus is getting reduced. One second. So copper 2 plus plus nickel will give you this. Okay. We need to find out at equilibrium what is the concentration of copper 2 plus ions. Which means we are assuming that this is at equilibrium. Okay. While this is reacting, in that case, the E cell will be equal to 0, which means E naught cell will be equal to 0.0591 by 2 log of K equilibrium, which is equal to 0.0591 by 2 log of equilibrium concentration will be nickel 2 plus concentration by copper 2 plus concentration. So nickel 2 plus concentration is already given 0.05 molar upon copper 2 plus concentration. This is the concentration of copper 2 plus at equilibrium. And E naught cell value can be calculated from the given E naught values. So E naught cell value will be equal to E naught of reduction at cathode and E naught of reduction value of anode. This is the oxidation value given. This is the reduction value given. So reduction value of copper is 0.34 minus reduction value of nickel is minus 0.25. Okay. So that makes it 0.59 volts. So you just have to substitute that 0.59 volts is equal to 0.0591 upon 2 log of 0.05 by copper 2 plus. Now you can see this almost goes 10 times here, correct? So I can write this as log of 0.05 upon copper 2 plus, right? That is equal to 20. So which is equal to 0.05 divided by copper 2 plus concentration is equal to 10 raised to power of 20, isn't it? So from here we will get copper 2 plus concentration will be equal to 10 raised to power of minus 20 into 0.05. So which is 5 into 10 raised to power of minus 22 molar. Got it? So now you can understand that it is hardly going to be present because you are already using excess amount of nickel in it. Okay, when you are using excess amount of nickel or finely divided nickel, hardly any amount of copper 2 plus will be present. Everything will get reduced. Please check it out. Finished, everybody? Let's see the next question. EMF of the cell is given at 27 degrees and at 37 degrees. We need to figure out what is the delta H value at 27 degrees. Okay. If you may recall the thermodynamic relations between E cell and delta H and delta S. So one thing we learned that, you know, delta S will be equal to, right? Sorry. First, let me write delta uh, G. Delta G is equal to delta H minus T delta S. And if you differentiate that with respect to temperature, we found this as minus delta S, which implies delta S will be equal to minus of d of delta G by delta T, which is equal to minus NF d of E cell by dt. Okay, and minus NF, this we can define as temperature coefficient, which is beta. I'll write it as beta for our understanding. Okay, so I just have to substitute that back now. Delta G can be written as minus NF E cell. Okay, that is equal to that will be equal to delta H minus T times of, correct, minus T times of uh, see, here it is about minus, right? That minus minus will get cancelled. I forgot to write that. Yeah. So here I can write this as NF into beta, correct? This is the value I have to write. So using that, I need to figure out what is the value of delta H here. So I can write this as delta H is equal to minus NF E cell plus T NF beta. So if I, the first thing we need to calculate is beta. So beta is temperature quotient. So what is the difference in the voltage with respect to the temperature difference? Check it out. So it is 0.002 minus 0.001 upon 10. Okay. So which is 0.001 by 10, which means 1 into 10 raised to power of minus 4. This is the beta value. Now, we were asked to calculate this at a temperature 27 degrees. Let me write down what is the overall equation here. So it is H2 getting converted to 2H plus 2 electrons, while AgCl of 2 moles is accepting 2 electrons to become 2Ag plus 2Cl minus. So then I can write the overall equation as H2 plus 2AgCl is giving 2H plus 2Ag plus 2Cl minus. So this will be the overall equation. Through this equation, we can say that n value is 2. N value is 2. So I need to just substitute that n value here in the equation or here in the equation to figure out delta H. So you can see delta H will be equal to minus NF is common. So minus 2 times of 96500 into E cell minus E cell minus T times of beta, which is equal to minus 2 into 96500 into E cell value at 27 degrees we know 0.002. So it is 0.002 minus T times. T is given as, because we need to find out at 27 degrees, it is 300 times 300 times that of beta, which is 10 raised to power of minus 4. So that is equal to minus 2 into 96500 and minus 0.002, and this will anyway become 0.0 3 0.03, correct? This is the value we will have, 0.03. Are we getting minus or plus? Let me just check that. T, if I take this minus here, and NF minus delta H of minus T times of E cell here, that is positive value. Oh, sorry, beta value I took it as positive beta, it is negative value. Please check. The difference is negative value here. So minus. That's the mistake I made. So beta is negative here. So minus minus will become plus. So here it will become plus. So that is equal to minus 2 times of 96500 into 0.02 plus 0.03. So which makes it 0.32. Now, this is the value I'll get, 0.32. We just have to multiply this value. So after multiplication, I mean, we multiply 96500 everything, correct? So I was getting this as, first I'll get this as 0.06 4 Faraday in joules. And if I actually multiply 0.064 into 96500, this value, let me just calculate and check. 96500 into 0.064. So that is coming out to be minus 6176 joules, or the answer usually will be reported in kilojoules. So this much will be in kilojoules. Okay. So this is very common question asked in JEE. So please check using temperature quotient how you calculate delta H. Okay. Take a minute's time, go through the question one. Calculate the equilibrium constant. Okay. For this, for a given electrode data through the reaction, if it is not a redox reaction. Okay. E naught value is given. This E naught value is given. We need to find out the equilibrium constant. Okay. So I suggest you try for a minute. Then I'll explain you how to. If you remember, I told you put three equations. Okay. So based on that equations, you will get to know. Got it? Which one? I mean, based on that equations, you will get to know how to relate delta G values. So try to relate the delta G values, and you'll be able to get it. Okay. So please try that for a minute. Notice how we can do this. Basically, you write the electrode equations for cadmium in both these cases. So how do I write that? Cadmium 2 plus 2 electrons is giving cadmium solid. Let this be equation 1. Similarly, cadmium 2 plus 4 moles of ammonia. Okay, okay, I'm okay. Will come. NH3, sorry, CD, NH3, 4 times and 2 plus. Got it? This is the formation equation. Clear? This is the formation equation. So let me put this as equation 3 first. I think that will be better. Two equation what we can write is, okay, NH3 4 times 2 plus 2 electrons. That will give you cadmium solid plus 4 times of NH3. Okay, 4 NH3. So this is the reduction value which is given, and let this be equation 3, correct? Now we need require to use this 1 and 2 equation to get 3. So let this be G naught 1, delta G naught 2, and delta G naught 3. Okay. So it's clear that delta G naught 3 we can achieve it by using 1 and then subtracting 2. So therefore we can write 3 will be 1 minus 2. 1 minus 2 implies CD 2 plus CD2 sorry, that is delta G naught 3 is equal to delta G naught 1 minus delta G naught 2. Now delta G naught 1 we can write it as minus N1 F E naught 1. Here it will be minus N2 F find anything about it, and E naught 2, while here it will be minus RT ln K formation constant, because it is about formation here. You can always keep this as the formation like this. Now delta G naught value will be equal to minus RT ln Kf will be equal to minus N1 F E naught 1 minus of minus N2 F E naught 2 F E naught 2. If I take this, you know that N value is common in all of them, so which is 2. So if I take it to the left hand side, I will get this as uh, RT by NF with ln Kf will be equal to, okay, E naught 1 minus E naught 2. Okay. So from there, you can calculate what is the Kf here. So therefore, ln Kf, sorry, this I'll write it as 0.0591 by 2 log of Kf is equal to E naught 1. E naught 1 value is given minus 0.41. So this is minus 0.41 minus of minus 0.61. This is the value of the second one. That's it. So therefore, this is approximately 0.03 into log of Kf is equal to 0.2. Okay, so this will be 0.2. So log of Kf will be equal to 0.2 upon 0.03. Correct? So which is around 20 by 3. So Kf will be equal to 10 raised to power of 20 by 3. Okay. So this is the value you are expecting. So please do check quickly. Now let's learn about electrolytic cells. I told you about this before. Electrolytic cells is about converting a non-spontaneous reaction, okay, into a spontaneous form. And it means in electrolytic cells, there is a non-spontaneous redox reaction carried out with the help of external battery source. So you can see, if I keep an external battery source, add two electrodes to the solution, and there is only one cell in this case, okay, then the left part of this is conventionally assigned as anode, right part of that is conventionally assigned as cathode. Now, since electrons are drawing through wires and coming towards cathode to get reduction done, so this time the cathode will be negative charged and the anode will be positive charged, which was reversed when it comes to uh, galvanic cells or voltaic cells. Correct? Now, listen up. Most of the time, when you do electrolysis through electrolytic cells, we always notice that we have to get a preference of ions, and that's what we call it as preferential discharge of ions. Okay, What I meant to say is, imagine you are having a solution in which multiple ions are present and they are all trying to go towards cathode, like A2 plus, B2 plus, and C2 plus. If they are moving towards cathode, and if this is their reduction potential, the reduction potential of this ion is -2, -1.5, and 1. So definitely based on the E naught values or the reduction values, it appears like C2 plus has a relatively higher value compared to the other two. Therefore, C2 plus has more chances to get preference over the others. So it will always be the first one to get probably reduced. Okay. So clear, you can see it is more preferred compared to the other ions to get discharged. This is called preferential discharge. Now you might ask, sir, what about other ions? Will they get reduced or not? Of course, they could also be, they could also get reduced. But priority is like first let the C get reduced, C plus 2 get reduced, then B plus 2 will get reduced, then A plus 2 will get reduced. Okay. This is what we need to understand how the electrolysis of aqueous NaCl works. So notice this. At cathode, what are the ions or what are the species they are competing? One is Na plus, the other one is water itself. Water is sufficiently polar, and when it notices there is an electrolysis, when it notices there are electrons approaching at cathode, water also has the affinity to go and attract those electrons. What is the reduction potentials? Sodium, to get itself reduced, the reduction potential is -2.71 volts, which is very less affinity, I would say, or you know, it will not intentionally try to go it unless there is huge amount of electron charge deposited, and then sodium alone has no competitor to go, so it will approach and get reduced. While water, if it takes two electrons and reduce, it will become H2 and 2OH minus. Okay, right? This I would suggest you write and learn as many times as possible, everybody, because I always notice students, you know, do forget how the reduction of water works. This is the reduction equation of water, everybody. Water will consume 2 moles of electrons to get H2, which is 1 mole, and 2 moles of OH minus in the solution. These two are competing. Now it's very clear from the values here that definitely water in competition will be more than sodium. So water will win over Na plus ion. So water itself will get reduced. Sodium will not get reduced. Now this is precisely the logic you apply for all the group 1 and group 2 elements, including aluminium. That is, if you take lithium, sodium, potassium, rubidium, cesium, magnesium, calcium, barium, strontium, and aluminium. So all of these 10 ions, everybody, if they are in aqueous solution, we can never reduce them using electrolysis. Why? Because water will always have much higher value of its reduction potential, that it will always overpower compared to the other ions. So we can never reduce them. That's why, everybody, if you want to extract these group 1, group 2, and aluminum metals, aqueous solution is never a preference solution or preferential solution. Because the minute you take aqueous solution, none of these ions will get reduced. Instead, water will compete with it and water will win over them. Clear, everyone? Now let's see what is happening on anodic side. We have chloride ion. When you are taking aqueous NaCl, we'll definitely have chloride ion. And of course, we have water. Water competes both at anode side as well as cathode side. Now see, water when it is getting oxidized, what is the equation you need to learn, mug up, whatever you do, you make sure that these two reactions are always learned thoroughly. One is how water's cathode reaction works, how water's anode reaction works. Water will always get oxidized to O2, giving 4H plus and 4 electrons, 4 moles of electrons. The E naught value for the same is minus 1.23, while the E naught value of chloride is minus 1.36. So comparing these two values, it is clear that the close edge is for water, right? That means we are expecting water to get reduced here also, theoretically. But practically, you will notice it is actually the chloride which wins. Okay. So practically it is the chloride which wins over water. So chloride will get easily oxidized as compared to that of water. Let's understand the reason behind it. See, according to the E naught values, water must be oxidized over chloride, but an exception will occur here due to a phenomena called over voltage. Okay, the term which you are looking out is called over voltage. Let me show you what is the difference in theoretical and practical values. Okay, now what's happening is water is trying to come to the electrode to get oxidized. These are inert electrodes, by the way. You can take steel, we can take platinum, correct, gold, any of these electrodes which are completely inert. Usually, for electrolysis of water, steel is most used. Okay, so basically iron electrode, but in the form of steel. So now water is expected to go and reduce here. What happens as the water comes close to it? You will see there will be bubbles of O2 forming as soon as it comes in contact with water, with electrode, because it will give away electrodes on the, it will give away electrons on the electrode and gives water, gives O2. So you will have a bubble layer of oxygen here on both sides. You will see this entire thing will have a bubble layer of oxygen. And this bubble layer of oxygen will not easily escape out to atmosphere. It will come very slowly out of it. Reason being, oxygen always being paramagnetic, have strong affinity with the metal. So the bubbles will start slowly moving across the metal. Of course, they'll come out and get, um, you know, get mixed with the atmosphere. But as they start moving across, it will be very slow movement. Because of which you will see a complete layer of bubbles forming and a new phase is being created here. So this said they we have completely water and right, and here it is solid state, but there is a new phase which is being created between them. Now because of which what happens now, water needs an extra energy to actually penetrate through this layer and then again come in contact with the electrode. So what we are doing here is, see, we are expecting water to carry an reduction oxidation potential of minus 1.23 volts. Okay, but it requires to have some over voltage, extra voltage, okay, of approximately zero point 0.8 volts. So overall, if you notice the E naught, sorry, this is bubble potential. BP means bubble potential. So that means overall, now practically how much it is required is around minus 2.03 volts. This much is the oxidation potential of water practically. Theoretically, this much is enough. But because of this bubble layer forming here, it requires that extra amount of push towards the metal surface. While in the case of chlorides here, so E naught value of chloride, correct, theoretically required is how much? Minus 1.36 volts, correct? But as it comes to the E naught value of bubble potential, chloride will make relatively much thinner phase here. Reason being, chlorine gas is not as so strongly attracted to metal surface as much as that of oxygen. Therefore, the bubble layer which is formed by chlorides is not that stronger. How much it is required? It is hardly requiring zero point 0.3 extra volts here. So which means E naught overall will be approximately minus 1.66 volts. So now you compare the E naught values here. So which will be better? So chloride will be having relatively better value, positive value as compared to that of overall voltage here. I hope you guys understood what is over voltage is. See, over voltage is always there in all cases. Okay, wherever there is a gas releasing. But if over voltage comes into picture only when the E naught values of the preferential discharges, these species which are competing, they are very comparable. See, unfortunately, here chloride and water are very comparable. That's why we are taking into account what is happening with the over potential or the bubble potential. Okay, and considering that, then we are looking at their practical values. Otherwise, in all other cases, the change, the difference of their potentials itself is very high. Like in cathode, the sodium value is very high compared to water, isn't it? So that's why water will get reduced easily. So there we don't have to consider how much amount of bubble potential or over potential is there. If the question is asked, is there any bubble potential? Answer is yes, there is always a bubble potential across the electrodes. But only if the competing ions have comparable values, then you consider practically if there is any difference that is going to make. Everyone clear with this part? Right. Now notice it. How do we write that in practice? How do we write this statement? I mean, whatever we discussed. See, this is in writing. What exactly or theoretically what happened? See, the transference of electrons from water is kinetically slow process, right? And it requires relatively large activation energy. Why is that happening? Because of that bubble potential. The slowness of the electrode reaction creates some electrical resistance at electrode surface. Hence, extra potential is required to provide that activation energy and to overcome the resistance in the case of activation of water, sorry, oxidation of water. Okay. So overall, this is the reaction. 2Cl minus is getting oxidized to chlorine. Water is getting reduced to H2 and OH minus. Okay. So E naught value will be minus 2.19 volts. Of course, it has to be negative only, right? Why negative? Because electrolytic cells are operated for non-spontaneous reactions only. For non-spontaneous reactions, E naught has to be negative. Now notice, in dilute solutions of NaCl, water can be oxidized at anode. If nothing is mentioned, always take Cl minus is getting oxidized. Okay. And at cathode, it is made up of, if the cathode is made up of mercury, the interesting part, instead of the steel electrodes, if at all we take mercury as the electrode, then sodium has a very strong affinity with mercury to form amalgam. So sodium will get consumed into, I mean, reduced into sodium. Ions will get reduced into sodium metal, and that will immediately mix with mercury and forms amalgam. Now, this time, water's affinity towards mercury is very less. So, therefore, those values which we have written, E naught values, those are only based on, those are only inference to hydrogen electrode, right? SHE. But here, with respect to mercury electrode, it is different. So, here you will see sodium has more affinity and that forms amalgam more easily. Okay. So, now you can see due to over voltage of H2 gas on mercury electrode, Na plus is preferred over water. Okay. And if you may recall, I mean, of course, you may not have learned it, but we will learn this again when we discuss S block elements. We will learn when you have to make NaOH solution, okay, in scale, right? If you want to manufacture NaOH from seawater, that is brine solution, then we use cathode electrode, then we use mercury electrode to do this process, okay? That is called Kastner-Kellner method. Okay, once again. Let's look into the next part, which is the electrolysis of copper sulfate aqueous solution. Again, I'm putting that disclaimer that it is about aqueous solution. If we take only copper sulfate, so it's a neutral solution, and we are taking, let's say, platinum electrodes here, both sides. All right. When there is copper, avoid iron because iron might get oxidized as well. That's why more inert one is platinum. And now you notice on platinum electrode, if water is getting oxidized, this is the value we learned already. But if sulfate is competing with it, because that is the other ion which is competing, then sulfate will basically convert into this peroxy sulfate. Okay, peroxy disulfate. So sulfate will oxidize into peroxy disulfate, and whose value is minus 1.96 volts. Now there is a sufficient difference between these two. So bubble point does not make a lot of difference here. Got it? So because based on the bubble point, this will have some value, this will have some value, but this value will be much more negative compared to this value. Therefore, who will win over whom? Water will always overpower over sulfate in the case of anode. While in the case of cathode, you will notice that water is getting reduced, okay, and copper 2 plus is getting reduced. If you compare these two here, in that case, you will notice that copper has, in fact, positive value, unlike water. So definitely copper will be the one which will be dominant here. Okay, copper will be the one which is dominant. So therefore, you are comparing this with this one. So this will be the cathode reaction. This will be the anode reaction. Okay, so you can see water, anode is getting H2 is getting O2 plus 2 electrons plus 2H plus. Cathode copper 2 plus plus 2 electrons and copper. Add both of them. This is the overall reaction. Okay, this is the overall reaction. Have you noticed something? Well, in this case, the H plus ion concentration is increasing, which means over the period of electrolysis, the pH value decreases. pH value keeps decreasing, the solution becomes more and more acidic. Next thing, this is the same method used for electroplating of copper. Okay, correct. And you see, copper sulfate is supposed to be a blue color solution in aqueous in water. Now, as the copper 2 plus ions will start decreasing, the intensity of blue color decreases over the time. And you see, on passing 2 Faraday charge, 1 mole of H2SO4 will be formed, and the pH of the solution will decrease accordingly during electrolysis, which I told you just now. Okay. Now, while using electrolysis using copper electrodes here, so basically what we do, this side, one side we take copper electrode, the other side we take platinum electrode. Okay, earlier case. But what if you take both of them being copper, right? And this is the important process we do in metallurgy also, that if you want to purify the copper, right, to make it ultra pure copper, you make one of the impure copper as the anode and keep the pure copper as the cathode. Okay, in that case, now you compare what is happening at cathode is, cathode definitely copper and water are competing, and copper will definitely win over the water. But what is happening at anode? See, on anode, in the impure copper, we will have iron, we will have copper, we will have zinc, we will have gold, we will have platinum. Okay. And now gold and platinum, they will never get reduced. Okay. At least not in these solutions. So they will always fall down of the copper here and, and make some kind of a metal mud here. Okay. It is like, a powdered form of metal, an insoluble metal that will be called as anode mud. Okay. So anode mud usually will have silver gold, and platinum. Okay, these three will be there. And inside these metal, copper, impure copper, we might also have iron and zinc. And if you notice the value of their iron and zinc here, did I write that values? No, I've not written that. Let me write down. Okay, reduction value of iron here, oxidation value of iron here. That is iron trying to convert into Fe plus 2. Correct. The E naught value is 0.56 volts. Okay, and zinc trying to convert itself into Zn2 plus, its E naught value is 0.77 volts, and copper trying to get oxidized, right, its E naught value will be minus of 3.4 volts, and water, if it wants to get oxidized to give O2 and H2 gas, we just learned that its value is minus 1.23 volts. Now, if we are competing, can you see that first iron and zinc will get oxidized? But since they are in a very small quantity, they will get oxidized and they'll stay in the solution. They'll stay as Fe2 plus or Zn2 plus in the solution. But later on, who will catch up? Then you can see copper is the one which will catch up. So copper is the one which will get oxidized now in comparison to that of water. So water never competes with these three now. So it will be eventually copper, large amount of copper which will get oxidized and large amount of copper which will get reduced. That's how purification as well as electroplating both are being done here. Copper, if you take copper electrode as the anode, it will over the time get completely dissolved and the same ions will get go and reduce here. So this cathode will be ultra pure copper only. Everyone, please do let me know if you have understood electrolysis with copper. Okay, so please read it once quickly here up to this part. Yeah, please read it. You can see if you take copper as electrode, pH of the solution and intensity of the blue color will not change with time because copper is being generated and copper is only getting reduced. Okay, and you see next electrolysis of acidic water using platinum electrodes. Okay, so if you notice the platinum electrodes and then we have dilute H2SO4 here. So what is the reaction that you will notice? See, at anode, these two are the ones which are competing. Okay, and at cathode, these two are the ones which are competing. Okay, just a second. Now let's see. If you have electrolysis of very dilute acidic water, okay, very dilute acidic water, and we have to use only platinum electrodes for this. So if I take a very dilute H2SO4, correct? In that case, what is happening at anode? See, anode, these two ions will compete, right? Cathode, these two ions will compete. What are these two ions? Look at it carefully. One is H plus and water. These two are competing here, correct? And here it is sulfate and water. These two are competing. Since the H plus ion concentration and sulfate concentration are not too high, so as long as they initially get consumed, you will see only they will get reduced. So which one will win over the other? First, this electrode will win, and sorry, here water will win. So which means at anode, water's oxidation is the first thing that is favored, and at cathode, H plus ion concentration, this will be favored. This will be happening, but in a very small quantity. I mean, not in the initial amount. Okay. Sorry, let me rewrite this part. Let me rewrite this equation a little bit. Hmm, Okay. See, this is 2H plus 2 electrons is giving H2 gas. So this would be more competing. This will be the overall reaction at anode. So you can see these two reactions will make the overall reaction is water itself. This 2H plus 2H will get cancelled. Water itself is giving H2 and half of O2. This is the overall equation, correct? Which means, can I read it this way, everybody? Check. We are using electron, 2 moles of electrons. 2 moles of electrons means 2 Faraday. And when I'm passing 2 Faraday charge, how much H2 I'm getting? I'm getting 1 mole of H2 and a half a mole of O2. This ratio will always be the same, everyone. So for every 2 moles or 2 Faraday charge, 1 mole of water is electrolyzed to give 1 mole of hydrogen and half a mole of oxygen at anode. So the volume occupied by the hydrogen at cathode will be equal to volume occupied, 2 times of volume occupied at anode at constant temperature and pressure. At constant temperature and pressure. Okay, clear? This is what you need to understand with dilute acid solutions. Correct? So please check this out quickly. Now, next look into electrolysis of molten sodium electrode. Okay, so you see, if we have two NaCl, okay, and you know that it will always be present in two Na plus and Cl minus. It will always exhibit in the ionic form when it is in a molten state. So at anode, there is only one ion now. At cathode also, there is only one ion now. So anode, this reaction will happen. Cathode, this reaction will happen. So overall, two Na plus and two Cl minus is, reducing and oxidizing in this form. So we can say 2 Faraday charge will produce 1 mole of gas of chlorine at anode and 1 mole of sodium, right, at cathode. Okay. I hope this electrolysis part is clear. I actually forgot to write one more part of it. So let me just add that also. So next one is about electrolysis of concentrated acidic solution. Concentrated acidic solution. Okay. So that means the water quantity is less here. So what we'll be expecting at cathode to compete? At cathode, definitely the main competitor is 2H plus 2 electrons is giving H2 gas. Which means what is that concentrated acid I'm taking? Typically, I'm taking concentrated H2SO4. And then you know that water is another competitor which is competing with this to get H2 gas plus 2OH minus aqueous ions. So this is competition at cathode. What about at anode? At anode, you see S2 SO4 2 minus is competing with S2O8 to become S2O8 2 minus plus 2 electrons, while H2O is also competing to become 4H plus O2 plus 4 electrons, correct? But now notice, based on the quantity, right? Quantity wise, this H plus is way higher. So based on quantity also, as well as based on the E naught value also, only this reaction will overpower. While at the anode, preferentially, you notice that water is supposed to get reduced or oxidized. But based on the quantity, there is large amount of sulfate quantity, because of which now this reaction will also start happening. Okay. Lot of time in the questions, you will be given some amount of percentages here. Like it will be given like the fraction, these two reduction is happening with a mole fraction of 1 by 4 and 3 by 4 here like this, correct? So this kind of information will be provided, because we can't really say only water is getting oxidized or only SO4 2 minus is getting oxidized. Because of the quantity wise, this is winning. Because of E naught value, this is winning. Okay. So overall, you always notice that the quantity will be the one which we are interested in. So quantity wise, this is the reaction that is happening at anode. Now, if I write the overall reaction, so what's happening here is 2H plus 2 moles of SO4 2 minus, that is becoming H2 gas plus S2O8 2 minus. Okay. So this is the overall reaction. Done. I guess all of you understood this part. Okay. So this part will always be given to you. Now, notice one thing. If you get this as uh, S2OA2 minus here, right? Now, the minute you add this to water, what will happen? See, these are the ions which are created here. Okay. So, in this overall reaction, if S2O8 2 minus is being added to water, so then what will happen? So first, you will see 2 moles of this will be utilized to get first H2S2O8 here, correct? First it will become H2S2O8, okay? And it has taken this 2H plus here, isn't it? So once you get this into this structure here, so we'll get S double bond OH here, and then we have OS double bond OH here, okay? Then again now, if you keep it in acidic medium here, sorry, if you keep it in acidic medium, let's say if it is in an acidic medium here, so in that case, we will have this, you know, water competing here first, okay, and this lone pair taking H plus here. So that way, you will first notice you will get this as H2SO4 plus H2SO5, okay, H2SO4 and H2SO5. This is when water molecule has been attached. So basically the OH minus part here is gone here, H plus part has been gone here. Okay. So that's what I am supposed to write this as first H2S2O8. That on hydrolysis will give you H2SO4 plus H2SO5. And now H2SO5, which is called as monosulfuric peroxymonosulfuric acid, that if you further hydrolyze, this will again become H2SO4 and H2O2. So that's how you can prepare peroxide also. Okay. So I'll write this in two steps so that you can understand easily. So first step is making this into H2S2O8, and then again on hydrolysis it will become H2SO4 and H2SO5. There is common name for this, if you recall. This is Marshall's acid, and this is Caro's acid. So first Marshall's acid is prepared, then Caro's acid is prepared, and from there hydrogen peroxide can be prepared. Hydrogen peroxide can be prepared. Okay. So this is how the electrolysis of concentrated H2SO4 works, everyone. Clear? Now let's let's see questions based on concentration cells, and then we will see the applications of the electrolysis, which we call it as Faraday's law. If you may notice, there is a sparingly soluble salt electrode on both sides. Okay. their Ksp values are given, their concentration of chlorides and bromides are given, and our objective is to find out what is E cell. If you have to find out what is E cell, then how do I do this? See, every time you have these kind of cells, right, the easier method, I would suggest always use that easier method. You assume that this electrode, okay, whatever the electrode, which is sparingly soluble form, you can assume it like a normal ion electrode. That is, you can use this as if it is getting oxidized to Ag plus aqueous ions, and on the other side also Ag plus aqueous ions is present, which is getting reduced to silver like this, which means the left hand part I'm replacing as this equation, right hand part I'm replacing as this equation. Okay, now it appears like a virtual concentration cell. Virtual concentration cell. So that becomes very easy to solve. How do we solve it then? For this virtual cell, we know that E naught cell will be equal to 0, which means E cell will be equal to minus 0.0591 by N log of log of Q here. So what is the Q value here? Because silver is getting converted into Ag plus plus 1. This is at anode concentration, while silver is getting Ag plus is getting reduced to Ag. This is at cathode concentration. So overall reaction will be Q is equal to Ag plus at anode upon Ag plus at cathode. Okay. So if I substitute this value here, then what do I get? So I will get this as E cell is equal to minus 0.0591 by 1 log of Ag plus concentration of anode upon Ag plus concentration of cathode. Okay. Now go back to the equation, original one. Here, there was no Ag plus concentration, and here there is no Ag plus concentration. But we know the Ksp value and C1 value. That's how you can get the information of Ag plus. So how do I get? Please check. We know that AgCl being sparingly soluble, it will be in equilibrium with Ag plus and Cl minus, and that will have Ksp, let's say Ksp1 here. So from here I can write Ag plus concentration will be equal to Ksp1 upon Cl minus concentration. Similarly, if we have AgBr, that will be Ksp2 doing Ag plus aqueous plus Br minus aqueous concentration. So therefore, here also Ag plus will be equal to Ksp2 upon Br minus concentration. So this is the anode part, this is the cathode part. So let me substitute that. So minus 0.0591 by 1 into log of anode concentration, which is Ksp1 upon chloride concentration into bromide concentration upon Ksp2. This is much easier way of solving the questions for E cell everybody. So minus 0.0591 into log of Ksp1 by Ksp2 into Br minus concentration by Cl minus concentration everybody. Okay. Now this way of solving unnecessarily avoids the information that is required in terms of what is the E naught value of this electrode, what is the E naught value of this electrode. That information is not essential. So if you want to calculate E cell, directly design a virtual cell and then calculate the unknown ions using their solubility product uh, equations. Okay. I hope all of you got the idea what I'm trying to say. Yeah. So once you get that, so E cell is clear here. Now you can just substitute the values which are being given. So here it is given as C1 and C2. So just put that values, you'll get the final equation. So which is minus 0.0591 into log of KSP1 by KSP2 into this is given as C2, C2 by C1. Okay. So that's how you can get E cell value. So everybody please go through it once. Let me know if you have understood the technique, what to do. Let's see. Design the same virtual cell here. Barium is going to give us barium 2 plus 2 electrons. Assume that this is the anode part. And then do the same thing with cathode. Barium 2 plus 2 electrons is giving barium. Assume this is happening at cathode. So in that case, E cell will be equal to E naught cell, which is 0 minus 0.0591 by 2 log of Q. So Q basically here is barium 2 plus concentration at anode upon barium 2 plus concentration at cathode. And using KSP, I can say KSP1 is equal to barium 2 plus concentration at anode into we have this as 2 times of F minus, right? So F minus whole square. So then KSP2 will be equal to barium 2 plus concentration, which is at cathode, multiplied by SO4 2 minus concentration. Substitute these values. E cell value is given as just a second. So notice this. We need to find out this at equilibrium. Hence, we can say E cell is equal to 0. So that is equal to minus 0.03 by 2. Okay. Log of this entire thing. So now you notice that this entire thing 0 means if I take this, I mean this entire thing will be 0 and everything will be equal to 1. So log of, barium 2 plus concentration at anode upon barium 2 plus concentration at cathode, that should be equal to 1. So barium 2 plus concentration at anode value will be from here to here. This can be written as KSP1 divided by F minus concentration square into this will be SO4 2 minus concentration upon KSP2. So KSP values are given, this entire thing is equal to 1. So from here I can calculate F minus by SO4 2 minus concentration. So yeah, F minus concentration square by SO4 2 minus concentration, that is equal to KSP1 upon KSP2. So take root on both sides. So I'll get this as F minus concentration by under root of SO4 2 minus concentration, which is equal to under root of KSP1 upon KSP2. So you can see KSP1 value is given as 10 raised to power of minus 6 and this is given as 10 raised to power of minus 10. So that makes it 100. Done. So same thing, we have used the same idea, putting a virtual cell, and from there we could figure out the relation between the concentration terms. I guess this is clear.